Hi there, welcome back. Today we're going to be talking about Newton's second law. We've been talking about linear motion this week. Lecture number 3 went over acceleration, velocity, speed, and we can use that to derive the very next step in the laws of motion that dictate everything around us. So here we have a picture of Newton admiring a nice t-shirt, and believe it or not, you can actually order these t-shirts online. That is actually Newton's second law, stated in pretty simplistic terms, and those will be pretty much the terms we'll be using. I'll add a little embellishment to it, but if you know F equals ma, you'll be just fine. All right, so some of the things that we need to understand is that force causes acceleration. This is actually common sense. Acceleration is directly proportional to net force, right? If you apply a net force to something, you're going to accelerate that object, whether it be, in this case, this gentleman pushing the bicycle and accelerating the child down the street, or if I'm taking a baseball and I'm throwing it, I'm literally accelerating it in my hand and releasing it and exerting a net force on it. And to increase the acceleration of an object, you increase the net force acting on it, right? The harder you throw the ball, which is to say the more force you put on it, the greater the acceleration. This guy here has to be careful not to put too much force, or he could accidentally give too much acceleration to this kid and he could wipe out on the ground somewhere off the picture. So we're talking about forces now, that there's a relationship between them, and one of the forces we've been talking about since the beginning is friction. Now, first and foremost, we need to say, yes, it's a force. A lot of people don't, it's not intuitive to you that friction is actually a force. And what is friction? Well, it depends on the kinds of material and how much they are pressed together. So imagine, I can take any two objects. For example, I happen to have right next to me a physics textbook, right? And I can put my hand on this physics textbook and I can push on it and my hand slides right across the surface. Even if I put a little bit more pressure on it, it slides a little more difficult, but it definitely does slide. But if I take my other hand and I put that together, I push with the same amount of force as I did earlier, and things are a lot harder to slide. And if I don't push with the same amount of force as I did on the book, it slides very easily. So the amount of force that I'm applying, or the amount of pressure that I'm applying on my hands, has a direct effect. Why? Because my hands actually have little bumps and crevices, things that impede the ability of my hands to slide over one another. Whereas the book, nice flat surface, very easy. All right, and that's basically what this says right here. It's due to tiny surface bumps and to stickiness, this is something I didn't mention yet, and to stickiness of the atoms on a material's surface. So not only is my hand got little bumps on it that is being resisted by tiny microscopic bumps on the surface of the book. Of course, those bumps are very small on the surface of the book. But the atoms in the book actually have electric charges that are attracted to the electric charges in my hand. And so they basically want to have a static electricity attraction, almost like when you rub a balloon, you put it on a wall. Okay? So a typical example would be, friction between a crate on a smooth wooden floor is less than that on a rough floor. Here's 6 men moving a crate, for example, and they're on a relatively smooth surface. You can actually see light reflecting off of it as they're pushing it along here. But if they were trying to push it, say, across concrete, or I'm sorry, not concrete, if they were trying to push it across, say, a wooded area or across a asphalt surface, this would be a lot harder for them to push it. It would be almost impossible. They'd need a forklift. All right, so another thing that we need to talk about quickly, we've been kind of beating around the bush on it, but we really need to approach this right now. And that is the difference between mass and weight. What are these two things? First off, mass is the quantity of matter in an object. It is also the measure of the inertia. Remember inertia? It's the resistance to motion when it's already set into a certain motion, or sluggishness that an object exhibits in response to any effort made to start it, stop it, or change its state of motion in any way. That's basically Newton's first law, right? This is not dependent upon gravity and not a force. This is very important. It's not a force. Mass is a scalar. It's true everywhere you go. It doesn't, you're not heavy in that direction or heavy in that direction or heavy in that direction. So it's certainly not a force. It can't be a force. You just have a mass, or the table has a mass, or your computer that you're watching me through has a mass. Okay? But it's not dependent upon gravity. Weight, on the other hand, is the force exerted on a mass due to gravity. A very different thing, right? So your computer that you're viewing me through has a weight to it. It also has mass. And it's basically the Earth's attraction to that mass that is exerting a force on that computer and keeping it on the Earth's surface. If that force didn't exist, you'd be able to flick the computer, and of course, it would float away according to Newton's first law. So let's look at this diagram down here. We have two astronauts, one on the Earth, one on the moon. It's actually the same astronaut, just traveled to the moon. The mass of the astronaut is 100 kilograms. Same thing here on the moon, right? Mass is a scalar. It doesn't matter where it is. But what about weight? Well, his weight, assuming the astronaut is a male, his weight is 980 newtons. And on the moon, it's only 162.2 newtons. And the reason why is weight is a force exerted on mass due to gravity. And the gravity on the moon is a lot less than the gravity on the Earth. Makes perfect sense, right? Not only are they different phenomena, one is a scalar and one is a vector, but they have different units. Regarding mass, the basic scientific unit of measurement is the kilogram. You're going to see the kilogram over and over and over again. We're going to talk about what the conversion of the kilogram is into other units here in a moment. Weight, however, the scientific unit of force is the Newton. Since weight is a force, it is also measured in newtons. We actually just showed that with the astronauts, right? The astronaut weighs 980 newtons on the Earth and 162 on the moon. However, the most common unit, which is to say the most common unit in the United States, is the pound. And the pound comes from medieval times. We have been using it for a long time. Most people are accustomed to thinking in terms of pounds. But pounds is a unit of weight, which is to say a unit of force. So this is going to be just something I would write in my notebook, just kind of something to have handy, is that 1 kilogram weighs 10 newtons. It's actually 9.8 newtons to be exact, right? We'll talk about how we know this here in a little bit on Earth. The relationship between kilograms and pounds is the following. 1 kilogram is 2.2 pounds, which is to say 10 newtons. They're all equal to each other. 1 kilogram equals 2.2 pounds, which equals 10 newtons. On Earth. And 1 pound equals 4.45 newtons. What does inertia tell us about mass and acceleration? The same force applied to twice the mass, and we usually use the letter m to denote mass, produces half the acceleration, a. You'll see a all the time. All right? What does that mean? That means that if I have two objects and one is twice as massive as the other object, and I push them with equal force, right? Say the one on the left is twice as heavy as the one on the right. That if I push them with equal force, I'll get half the acceleration on the heavy object relative to the acceleration I get on the lighter one. And 3 times the mass produces 1/3 the acceleration. So what does that mean? Acceleration is inversely proportional to mass. And so there's the proportionality measurement. This is the mathematical way we would write that. Mass is proportional to 1 over the acceleration, right? The inverse, 1 over anything, is the inverse or the reciprocal. And so just in case you forgot what inertia is, study this image right here. This guy has clearly hit the brakes either too hard or hit a mud puddle or something like that. And these 3 girls are watching him look very foolish. So So that all leads us to Newton's second law of motion. We built up to what this is all about. So Isaac Newton was the first to connect the concepts of force and mass to produce acceleration. And he did this when he was just 23 years old. Newton's second law, the law of acceleration, relates acceleration and force. So in other words, he's the first one that says that acceleration and force are very related. But they're related through a very interesting mechanism that nobody thought about. So this is the law. The acceleration produced by a net force on an object, so acceleration being pushed, right? So the acceleration being produced by a push on an object is directly proportional to the net force, right? The harder you push on something, the more of an acceleration you're going to get. That's really all he's saying. Is in the same direction as the net force. So if you push on that object, it's going to go the same direction. It's going to accelerate in the same object as the push. And is inversely proportional to the mass of the object, just as we stated on the previous slide. So while the acceleration is in the same direction as the force and is directly proportional to the force, mass plays an important role in this equation, that it's inversely proportional to the mass of the object. Why? Because you have to incorporate inertia into the equation. And he was the first one to do this. Absolutely impressive that he could come up with this. We'll talk a little bit later on when we talk about something called momentum, how he actually came up with this. So yeah, I'm impressed by me too, and he should be. Actually, he was a very humble person about his discoveries, and he didn't really like to toot his horn too much about it. He was very private and very quiet about a lot of things. But I'm impressed. All right, so how would we write that out? Because in equation form, it makes a lot more sense. So in equation form, it's just acceleration equals force divided by mass, right? And force is always the net force divided by mass. Or most famously written as force equals mass times acceleration. It's so famous, this guy actually wrote it on his arm, right? So it's probably the most famous equation in all of science, right alongside Einstein's famous equation, which is tattooed on his other arm, okay? F equals ma and E equals mc squared. You'll be learning both these equations in this class. This one will come right at the end of class. This one will be something that you'll be seeing throughout basically the first half of the class. So suddenly, things like gravity make sense with the second law, right? If you incorporate inertia into the equation, everything starts to make sense. We have two blocks, the free fall of two blocks, which is F equals ma in action. Remember, acceleration due to gravity, we would call that g, F equals mg. And that's what we're seeing right here. F equals mg, it's just rewritten as F over m equals g. So there's two objects, one of mass m and mass 2m, right? So let's go through the logic here. The greater the mass of the object, the greater its force of attraction towards Earth, right? So mass m is going to have an attraction of F, but mass 2m is going to have one of 2F. But it's also going to have greater inertia, right? So here's m. Remember, m is taking into consideration that inertia component, but this is 2m over here. And when we do the math, it's pretty obvious that you can put, you can cross cancel the 2 over the 2, and it just reduces F over m equals g. F over m equals g. They're the same thing. In other words, g here and g here are equal. So, and that's what this says here. So acceleration of both sets of bricks is the same. Twice the force on twice the mass gives the same acceleration, g. The acceleration of both sets of bricks is the same, 10 meters per second squared, right? So that it suddenly explains why Galileo was able to go to the Leaning Tower of Pisa, drop a heavy object and a small object off of the top of it, and they landed about the same time. The heavy object has a much greater attractive force to the Earth, but it also has a lot more inertia. It resists that acceleration, whereas the smaller object has a lesser attractive force, but it's also more likely to fall because it doesn't have as much inertia. So that suddenly ties everything together. Inertia, gravity, force, mass, it's all linked. So non-free fall ball. All right. So we were just talking about a situation where it's in straight free fall. So when an object falls downward through the air, it experiences two things. It experiences the force of gravity pulling it downward. We would call that, remember, F equals ma, but we know that ma is actually mg because it's gravity. A is the same thing as gravity. So here we see mg is the force of gravity pulling it down. And air drag force acting upwards, which is usually marked as an R, meaning resistance. So it should say resistance here. This is a rock that's falling. So these are the two forces that we need to keep track of as this thing falls. I thought this was kind of a cool little picture off the internet. A cow caught up in a landslide falling on a car. Again, mg going down this way, resistance going up towards the top. So I like this. Little sign, and I would put it on my office door if I had one. All right. So the condition of non-free fall occurs when air resistance is non-negligible. So when does that happen? When does air resistance become non-negligible? I mean, if I just take this pen and I drop it onto the table, is it non-negligible or is it negligible? Well, it turns out that if I just drop it a short distance, I can ignore it. And the reason why is two things: speed and frontal surface area of the object that is going through the resistance. So if I drop it right to the table, it's not falling enough of a distance to get enough speed where I have to worry about air resistance. But if I'm dropping it, say, from the top of the Grand Canyon, I definitely have to take it into consideration because the speed is going to be very great. Even at the frontal surface area, the pen is falling like this. It's still going to get a very large speed. Now, is it going to fall faster this way or this way? Well, if it's falling this way, it has a much smaller, I almost said larger, a much smaller frontal surface area. So it's going to go faster. Whereas if it's falling on its side, it has a larger frontal surface area. In other words, it's falling like this. It's obviously going to be slower. Okay, so we have a good idea of what the two principal forces on this falling rock are. There's the force due to gravity, there's resistance going in the opposite direction, and let's see what happens when it starts going at a very high speed. When the object is moving fast enough such that air resistance builds up to equal the force of gravity, then there is no net force, right? Because they're balanced. The force of gravity is balanced by the air resistance. What happens? Since there's no net force, that means there's no acceleration. In other words, the rock stops speeding up. The velocity does not change. And the math is pretty straightforward when we look at that, right? So F equals ma, or the sum of all the forces. So there's two forces. There's gravity plus negative resistance. Remember, the negative sign means it's going the opposite direction of the falling rock. So mass times gravity plus and negative r. But we already know that mg is equal to r. Why? Because it says it right here in the text. Air resistance builds up to equal the force of gravity. So they're the same. So you're really just taking two quantities that have the same value and subtracting them one from another. So in this case, the net force is equal to 0. So no acceleration, velocity does not change. What does that mean? It means we've acquired terminal velocity. Terminal velocity occurs when acceleration terminates, when air resistance equals force and net force is 0, right? We're headed right back to that whole idea of Newton's first law. It's the same thing as terminal speed. You'll hear that a lot mentioned amongst parachutists, with direction implied or specified. So I hope you have a good understanding of what we've been talking about with Newton's second law. So before we kind of finish this, I thought it'd be fun to do some sample problems. One would be, for example, how much force does a 50 kilogram crate exert on the ground? Okay, so I'm going to go ahead and open up another program, and we're going to solve it there. Okay, so I thought it would be fun to use a virtual chalkboard. I've never used this program before in a lecture, and I thought I'd try it out. So we want to know how much force a crate that weighs 50 kilograms, the weight of our crate, how much weight is exerted on the ground. Now we're assuming that the crate, right? The crate is sitting on the ground. Go ahead and put some boards on it. And we want to know what the force in this direction is going to be. Okay. So it should be pretty straightforward, actually. We use F equals ma. Okay, so we want to know the force. Oh, we got to always remember our little symbols here. All right, so we know that the mass is 50 kilograms. I'm going to multiply by some acceleration. What is the acceleration we're going to use? Well, remember, acceleration in a gravity field on Earth is equal to g. And g is just equal to (10 meters per second squared on Earth. 10 meters per second squared. So the force is just equal to 50 times 10, 500 kilogram meters per second squared. And you might be saying, this is strange. What is this kilogram meters per second squared? Well, it turns out that the kilogram meter second squared is also known as a Newton. So you've seen this before, right? I just didn't tell you that a Newton was equal to kilograms times meters divided by second squared. And it's hard to think in terms of that. So the unit that we use for that is the Newton. And so the answer is F equals, or the force is equal to 500 newtons. Okay? So I hope that that's an interesting one. Let's see if we can do another. These are pretty fun. So the next question is, what is the mass of an object that weighs 75 newtons? This should be pretty straightforward. This is F equals ma as well. Let's solve that one. Okay, so we're back to our virtual chalkboard. F equals ma. And we know that F is equal to 75 newtons. We want to know the mass. Well, the one thing we do know, before I continue this thing, is what the acceleration is. It's implied because this is going to be on planet Earth, where we live. And in that case, it's equal to g. And since we know that 75 newtons equals mass times g, we know that g is equal to 10 meters per second squared. And we know that newtons are equal to this really interesting unit called kilogram meters per second squared. We can divide both sides by 10. Okay, and we can do very rapid division, right? This cancels, second squareds cancel because they're both in the numerator and the denominator. Mass cancels, it's in the numerator and denominator. What's 75 divided by 10? Yeah, you guessed it, 7.5. And 70.5, the only thing that hasn't canceled out yet is kilograms. So our answer is 7.5 kilograms. All right, this is really fun. I actually want to do one more. Let's do one more. All right, so here's one. How many newtons of resistance are required to bring a ball with a mass of 5 kilograms to terminal velocity? Wow, that sounds like something we've been actually doing the last half of that lecture. So let's see what newtons are. First off, newtons, remember, is a force. So we know that we're going to be adding up forces. So how many newtons of resistance are required to bring a ball with a mass of 5 kilograms to terminal velocity? Okay, you might be able to do this in your head. Let's see if you're able to. But I'm going to go ahead and work through it anyway. So we always write our equation first. F equals ma. Okay, we know that m is equal to 5 kilograms. So what is the story? What is actually happening here that we need to be thinking about? Well, there's a ball. It's falling through the air. There are two forces. There's a downward force that is equal to mg, right? Mass times gravity. That's the force of gravity upon the ball, right? And we're going to call this m. That's the mass. And then going the opposite direction is a force that is opposing it, and it's equal to r. Now, we're told right away that we want to know how much resistance, what is the force of the resistance required to make this come to terminal velocity? All right, well, the sum of the forces on the mass that is falling, this ball that is falling, is mg plus r. But r is negative, right? R is negative because it's in the opposite direction from mg. Plus a negative r. All right. So simply put, if I know what mg is equal to, and I want this whole thing to equal 0, right? So simply put, I want the net force to equal 0. So if the net force equals 0, which means it's at terminal velocity, mg plus a negative r. This can be solved by simply adding r to both sides. So I'll just put a plus r there, plus r there. And when I do the arithmetic, I get r equals mg. So you can see in your mind pretty rapidly what it has to be. Well, I already know what m is. I know what g is. M is 5 kilograms. G is 10 meters per second squared. And I can already see that 5 times 10 is going to be 50. And kilogram meters per second squared is just a fancy way of saying newtons. 50 newtons. That would be my solution for this. Okay, I hope you like those. Those are really fun. And I'm using a virtual chalkboard. I hope this works out. Cool. So I hope you really enjoyed playing with some of these formulas. Don't let it get too frightening. You know, this is really fascinating stuff. But once you start to think about how force and mass and acceleration are related one with another, one, you'll appreciate Newton for coming up with this, because it's amazing that a single person by the age of 23 could have figured this out, let alone to figure out the first law. And we're just beginning to scratch the surface of some of his accomplishments. But the two useful formulas that I want to make sure you know are going to be acceleration is equal to force divided by mass. And then, of course, this is just a restatement. This is the famous form of this earlier equation. This is actually what he found here. And then force equals mass times acceleration is the more famous version. And remember, a Newton, which we usually call an N, is just a kilogram times meters divided by seconds squared. So anyways, I hope you enjoyed this. I know there's a lot, it might be a little convoluted, might make your brain ache a little bit. Newton's second law is sometimes Not as intuitive as it appears on the surface, but I hope you enjoy it. Think it through, and if you have any problems, feel free to contact me.